Hi y'all, here's another domain example. I want to look at one more pair of functions. So we want to find the domain. And the first function I want to look at is f of x. Okay, so if we would like to find the domain of this one, for starters, this on its own is tricky, and then we are going to compare it to another function and see something that happens that's interesting. Okay, so the reason this is tricky, it's not so hard to figure out what I'm worried about. I'm worried about square roots of negative numbers. So I have a radical, I don't have a fraction. If you don't have a fraction, you're not worried about zero. Square roots deal with zeros beautifully. But you are worried about taking the square root of a negative number. So basically, I want to figure out when x squared plus 7x plus 12 is greater than or equal to 0. So there are algebraic ways to work at this, and I can even mention them. I think I gave you something factorable. Let's see, factors of 12. Yeah, 3 and 4. So x plus 3, x plus 4 is greater than or equal to 0. So what's tricky here is that you can't just go isolating x because there's more than one x floating around. Even if I had something like this, x squared plus 12 is greater than or equal to 0, I'd be in some trouble because, well, actually I'd be in trouble because I'd get x squared is greater than or equal to negative 12, which is kind of a weird statement. But anyways, square rooting both sides, even if you got a positive thing over here, is trouble because when you square root both sides, you get this plus or minus, and that's totally going to mess with the direction of your inequality. What exactly should happen with direction? So we can try factoring. Factoring doesn't do anything to mess up our inequality, but this becomes kind of a process of elimination. If you're multiplying two things together and you want to make sure they're positive, then you either want to make sure that both factors are positive or both factors are negative. So we would be in trouble if the first one is positive and the second one is negative, or if the first one is negative and the second one is positive. This can be figured out. If you want to just try and figure out when that happens, that's fine. Here's my advice. I think this is easier. You can agree or disagree. I would say let's think about the graph of y equals x squared plus 7x plus 12. So I'm basically just naming this whole thing y, and I'm going to look at a picture of it. All right, I've already figured out the factored form of this is x plus 3, x plus 4, which means this function has intercepts at negative 3, negative 4. And since this is a positive x squared, I should also know that this thing opens up. So this is really rough sketch, but that's okay. That's all I really need. Okay, so this is what my function looks like. Again, not my original function. My original function has a square root. I've stolen the part of it that's under the square root, and I'm looking at it all on its own. Okay, so really what's happening here is I want to look at taking the square root of this thing. So the square root of the whole thing, which means the square root of my y values. If I want to be able to take the square root of my y values, I need to make sure that my y values are greater than or equal to 0. Another way to get at this is to say, okay, if I'm trying to solve x squared plus 7x plus 12 is greater than or equal to 0, and I name x squared plus 7x plus 12 y, then I can just replace all of this with y and translate the statement into y is greater than or equal to 0. If we can figure this out, this is usually the confusing part with people. If we can figure out that what we're doing is taking this whole thing, setting it equal to y, and then trying to figure out when y is greater than 0, we should be able to get that from the picture. It looks like my y values are going to be greater than 0 if my x's are greater than or equal to negative 3. So that's this chunk right here has positive y values, non-negative y values. Or if my x's are less than or equal to negative 4. That's this chunk right here. So really, we just want to leave out that little bit in the middle where the graph dips below the x-axis. And this is our domain. So we want to say we want all x's less than or equal to negative 4 or greater than or equal to -3. And if you want to be formal about it, throw on some set brackets. And again, this should be an or, not an and. There's a difference. Or is like our union symbol. It means the combination of those two sets. If we said and here, we would be talking about the overlap of those two sets, and those two sets actually don't overlap. The numbers bigger than -3 are automatically not smaller than -4. So and would be a bad choice here. If you prefer your interval notation, you would say I'm starting at -infinity and I'm going to -3. Perfectly acceptable to include -3. -3 makes y equal 0, and that's fine. I can take the square root of 0. I then want to leave, oh, sorry, I got myself backwards, guys. I'm going to -4 if I'm looking at my graph. There we go. So -infinity to -4. We then want to leave out everything between -4 and -3. So we're going to start back up at -3 and go to infinity. Just like before, it's completely acceptable to include -3. I can take the square root of 0, so no problem. Okay, so kind of messy, but basically what happens is linear inequalities are pretty easy to solve. If you remember that multiplying or dividing by negative number switches directions, you otherwise just solve it as if it was an equation. If you get some messier inequality, if it's quadratic inequality or a cubic inequality, or if you have a rational in your inequality, you're going to have to be really careful. And graphing can be a really good way to sort that out. If you snag whatever you're trying to set greater than or equal to 0 and graph it, you just need to translate this statement as a y greater than or equal to 0 statement. All right, so that one was messy enough, but I also want to compare it to one other. So let me give you this, and then we'll talk a little more about it. Let's call it g of x. And let's make it the square root of x plus 3 times the square root of x plus 4. Okay. So same directions. I want to find the domain of this thing. And if we look back above, in fact, I'm going to rewrite here. I'll use the red pen. We decided that a quadratic that we had under the square root of above factored into x plus 3 times x plus 4. So there's definitely some sort of relationship here. This is another one of those where our functions are algebraically equivalent. According to the rules we learn in algebra, you can split a square root over a multiplication. So if you have the square root of a product, you can split it into the product of 2 square roots. Or vice versa, you're supposed to be able to take the product of 2 square roots and mush it together and make it the square root of the product. We're trying to get a little smarter. That's completely valid, and I'm not taking that away from you, but you have to know about some of the pitfalls involved with this. So that's what this domain stuff is all about. Okay, so if I'm taking the square root of x plus 3 multiplied by the square root of x plus 4, and I want to figure out the domain of this thing, this is actually a setup that involves 2 simpler statements. To be able to plug an x value into the first radical, I need to make sure that the x plus 3 is greater than or equal to 0. Can't take the square root of a negative number, which means the x needs to be greater than or equal to -3. Okay, so I can plug an x value into the first radical and get an answer as long as the x value is at least -3. In order to survive the second radical, I need to make sure that x plus 4 is greater than or equal to 0. So x has to also be greater than or equal to -4. And it really isn't also. If I choose an x value that is, let me think about which one I can actually do, bigger than -4, but it is not bigger than -3. So for example, think about x is equal to -3.5. Then when I go to plug it in, it's going to work perfectly well here. I'm going to get the square root of 1/2, which I can handle, but it's not going to work here. I'm going to get the square root of -1/2. And if either of these square roots gives me an imaginary number, doesn't give me a real number, then I'm out of luck. So this is not an OR. I don't want the combination of the 2 sets. I want the intersection. I want all of the values that make both square roots happy, which means I need to only take the x values bigger than -3. If something is bigger than -3, it's automatically bigger than -4, so this square root is going to be fine as long as this square root is fine. Which means really all we have to say is choose an x value bigger than -3 and you're in good shape. So based on this, we can ask the same question. Are f and g equivalent functions? And the answer, once again, is no. They are algebraically the same. Algebra properties of radicals says we should be able to mush those together, but we can run into trouble if we're not careful about what x values we use. So they are identical as long as x is greater than or equal to -3. If x is less than or equal to -4, you're going to have output values for function f and no output values for function g. So they do differ for all x's less than or equal to -4. All right, thanks for watching.